through a couple review problems. Remember when you simplify a square root, especially when you're not, when you're familiar with, you're just going to look at factor pairs. Like 81, for example. If you want the square root of 81, you could do a whole factor tree and work that out, or you could look at factor pairs, 1 times 81 and 9 times 9. That's your factor pair. It turns out you could use a factor tree for that. For every pair that roots up, you take out 1 to represent it, and that's your square root. So, hold on to some, let me do a couple of things. Like, suppose you have a, we're only going to do perfect squares today. Things that come out perfectly. Suppose you had, yes, 100. Of course, there's so many ways to do a factor tree. You could do 2 and 50 to get a prime factorization, 2 and 25, and 5 and 5. Or you could look at factor pairs, 1 and 100, you know, and you'd go through all your factor pairs, but eventually you would find 10 times 10, right? The goal is to figure out, is there a number times itself that equals what's inside? And if there is, then the square root simplifies completely. But sometimes you're going to see people use factor trees, and I want to show you that because the factor trees also work, and they're a little harder for this method, but they are essential when you don't have a perfect square, which we're going to build to. But we're not going to build to that today, but I'm going to just show you. Should you use a factor tree, do you see this pair here? And do you see this pair here? What's 2 times 5? 10. So you could also, if you just like factor trees and you're not sure, you could also do factor trees. Because there were some problems I was starting to do the other day that we didn't have tons of time on. Like, let's say 625. Sometimes you don't know the factor pair. You just might not know it. So you have to decide, is this 625 a perfect square? And sometimes the quickest way is just to establish a factor tree and not just list all the factor pairs. Because listing factor pairs, when the number is big, can be time consuming. So use a factor tree. So 25 goes into 600. Well, how many times does 25 go into 100? So how many times does it go into 600?
24. Oh, well,
24, right? So how many times does it go into 625? So, okay, so that's one method, right? But suppose you don't figure that out. That tells you right now that this is 25, but maybe you don't figure that out, and your strategy whenever you see something that ends in 5 is to just go 5 and then use maybe short division. 5 goes into 6 once. There's a remainder of 1. 5 goes into 12 twice. There's a remainder of 2. 5 goes into 25 5 times. And then you continue your factor tree. Doesn't 5 go into 125? How many times? 25, right? And doesn't 25 break down? 5 and 5. So here's a pair, and here's a pair. What is 5 times 5? 25. Okay, then we're going to estimate today. It's like I paid you to ask that question. Oh, maybe also because I wrote it down. Okay, so let's pick. Let's make sure we all understand what it looks like when there isn't a pair. Okay, what if we had like the square root of 80? If I tried to break that down, I could do like 8 times 10, 2 times 4, 2 times 2, 2 times 5. So there are pairs, but there aren't all pairs. So for today, you're going to estimate instead. Do you understand what it looks like when it's not a perfect square? There's a leftover, so it's not a perfect square root. You see that? Yes or no? Okay. Okay, you can get even better. You're going to be able to estimate accurate to the 10th place without a lot of work. Not a guessing situation like the homework last time. Okay, so first thing that's handy is it's very handy to know your perfect squares. All the way to 25 is what I would recommend. I am telling you what, for the rest of your education, knowing these, they're never going away. You can figure them out, but they're always going to be with you. Up to 15 this week would be great. You already know up to 10, 12. Question?
Well, in 5th grade, we had to memorize.
I remember you said that.
Up to 25, and then we would take like
Time tests.
Like 5 minutes.
It's so helpful to know these forever. It's just helpful. So learn them. 1 squared, 2 squared, because then going backwards, if I asked you what the square root of 64 is, of course you guys already know 8, but if I asked you what the square root of 289 is, it would be, remember it? It ends in a 9.
17.
Right. So 7 times 7 is 49, so you don't have a lot of choices. That's how I do it. I don't, like for example, if I knew 289 was a perfect square, I know I would go through the thinking I talked about earlier. I'd say, well, 10 times 10 is too small. 20 times 20 is too big, right? So I need numbers. I need to look at the numbers in between. I need to look at 11, 12, 13, 14, 15, 16, 17, 18, and 19. Do you guys know why? Because 10 squared is 100 and 20 squares 400. I'm going to wait till you guys are listening. Johnny, put your feet down. You got to pay attention. Okay. So you may think that those numbers are a whole bunch to test out, but you know that when you multiply 11 times 11, the last digit's going to be 1, so it can't be this. 12 times 12, the last digit's a 4. What's 13 times 13?
169.
So, no, right? 9 times 9 is 81, so this one can't be it. 8 times 8 is 64, because 17, so 7 times 7 is?
49.
So it might be that. 6 times 6 is 36. 5 times 5 ends in a 5. 4 times 4 ends in a 6. The only possible number that could be a perfect square, if 289 was a perfect square, is the 17. And we just did that a minute ago. 17 times 17 is 289. So it's not that hard to memorize them all. Adam.
Why'd you, like, I understand that it isn't 13, but why'd you eliminate it? So,
Because he already knew, he said 13 times 13 is 169. But really, right, those are the only two you should consider, and then you would throw that out. So, for example, so that's what I mean. So memorize them. Matthew.
yeah, I always had a trick on 13 and 14 because it was like the two past what you normally learn.
Right. 12 was usually the last thing you learned in elementary school.
Yeah, so and for 13 it's 169, and then you just reverse the last two digits.
Oh, I never did that. That's a great idea. Good idea. Yeah. 13 is 169, 14 is 196.
Oh, that's smart.
That is smart. Okay, so do you understand so far the goal today, if we look at the other page, is you definitely need to simplify, boys. You need to simplify square roots. You need to decide, like in this case, if they can't simplify, that you have to make an estimate. And then the next thing is, I'm going to show you how to do a good estimate and why it works. And then we're going to go over the last week's test. Okay? So, is everybody good on the goals? So we're going to practice estimating to the 10th place. You'll be surprised how accurate this is. So, when you look at this page here I have set up, so like Adam asked last week, what's so special about the square root of 2? It's not any more special than the square root of 3. It's just that it's a low square root, and so people, talk about that as one of the early irrational numbers that you learn. That's all. There's a whole bunch of them. But square roots basically are the dimensions, perfect squares are the dimensions of a square. So like 1 by 1, 2 by 2, 3 by 3, 9's a perfect square because you can make a square shape out of the same number to get an area of 9. This square has an area of 4, so you can make a square shape. A rectangle, you can make a square that has an area of 4. And 1's a perfect square. So in contrast, if I wanted to do 2, if I wanted to do something the area of the 2 with an area of 2, there's no integers, non-fraction numbers that I could put on the side to make the area of 2. That's why it's not a perfect square when you take the square root of 2. So here's this idea that works great, but you have to kind of watch for a little bit. I'm going to do 3 examples before you guys can ask questions. Just watch it. If I want to estimate the square root of 2, I'm going to figure out what it falls between. So I know it falls between the square root of 1. What perfect numbers it falls between? The square root of 1 and the square root of 4. Does that make sense? So we know the square root of 1 is 1, and we know the square root of 4 is 2. So logic would tell us this is going to be 1 something. Okay? Just let me go through the whole thing. You can guess in your head, but I want you guys just to let me go through the whole thing. So there's a little geometry to this. If you take the square root of 1 and you think about the square root of 4, do you guys agree, like, I need 3 more squares to get from the square root of 1 to the square root of 4?
Yeah.
Right? You get that? I need 3 more squares. So watch what I'm going to do with that. I'm going to put a fraction here where this is a 3. And I know 2 is, I want the square root of 2. So I'm 1 square on the way to the 3 I need. Because the square root of 2, I've got 1 more square than the square root of 1, this purple square. But I need all of these squares to get to the square root of 4. So I'm 1/3 of the way to the square root of 4. You got to let me do more than 1 for this to make sense. But I just wanted to show you on the calculator, if I type in the square root of 2, the bigger the number, the more accurate this is. So 2, and then the square root of it, it's 1.4, okay? My estimate gives me 1.3 repeating. You see that? It gets better with bigger numbers. So watch. If I want to do, you got to let me do a few here. If I want to do the square root of 5, so I'll show you the other page while I do this so you can look at the similarities. If I want to do the square root of 5, do you guys agree it falls between the square root of 4? The closest perfect squares are the square root of 4 and the square root of 9. So the idea is you want to look at the square root of 4 and make that into a square root, a 9 size area. Okay? I need 5 more squares. 1, 2, 3, 4, 5 to get from 4 to 9. Do you see that? So I know that the square root of 4 is 2, square root of 9 is 3. This has to be 2 something. And out of the 5 squares that I need to get from an area of 4 to 9, I already have 1, because the square root of 5 is 1 more than the square root of 4. 5 is 1 more than 4. So my estimate is 2 1/5. 2 point what? It's about 2.2, right? So if I pull my calculator up, and take the square root of 5, I get 2.23. It's not bad. Better than what I was doing in homework, right? Just kind of guesstimating. Now watch. What if I wanted to do, say, the square root of, let's do 14. That falls between what? What perfect squares? 16 is one of them, right? And the one below it? 9, right? So the square root of 9 is 3. Square root of 16 is 4. So this is going to be 3 something, right? Well, I have to take my 9 size square and build it up to a 16 size. Do you get that?
Will we have like graph paper and extra clips so we could?
You could use graph paper. So to get from 9 to 16, though, Olivia, you also really don't need it, because how many squares do you need to get from 9 to 16? 10, 11, 12, 13, 14, 15, 16. How many squares is that? 7. So you always can figure out that 7. Okay, but 14, so this is 9 squares. 10, 11, 12, 13, 14. I have how many of the 7 I need? I have 5. So 3 and 5 sevenths. Now, you could leave it like that, but let's just, on a calculator, let's talk about 5 sevenths here. What is 5 divided by 7? 0.7, roughly? Okay, so I was trying to do the square root of 14, right? 3.7.
Whoa.
Pretty darn close, right? So Olivia's got a valid point. What if it's like a huge number and you don't have graph paper? Well, where is the 7 coming from when you look at 9 to 16? How far apart are they, Johnny?
7's coming from how much you add to get.
From 9 to 16. 16 take away 9 to 7. Where's the 5 coming from? Yeah. Yeah, a perfect square is 9. I have 5 more units than a perfect square.
Oh.
But the reason I'm showing you the picture is that if I just do this over here, it's like some little rule. It really comes from logic.
How do you get the 3 again? Like 3.5.
Because the square root of 9 is 3. The square root of 16 is 4. Since 14 falls between 9 and 16,
Oh, yeah.
it's got to be in the middle of 3 and 4, or in between. So watch without a rectangle. If I want to do the square root of a bigger number, let's say 37. Okay? What's the square root that's perfect right below it?
36.
And right above it?
49.
49. So your answer is going to be way closer to 6 than it is to 7. So I'm going to think about it. To get from a perfect square of 36 to a perfect square of 49, I need 13 units. I've only got 1. That's my estimate. You can leave it in fraction form, but let's check it with the calculator.
Whoa.
1 divided by 13 is 0.08, roughly, right?
Whoever invented math was a genius.
So if I want to do the square root of 37, .08, it's 0.08.
Like a really good.
It's about, well, that's all we have time for right now, because I want to answer questions on the test. But I can do more later. Okay, your homework is not on the Pythagorean theorem. It's on the same page as it was Friday.